Hi everybody and welcome to my video on calculus. This video is going to talk about some of the background, the history leading up to um, the discovery or invention or foundations of calculus. We're going to focus less on Isaac Newton and Leibniz than other videos might. So we're going to talk a little bit more about antiquity and history and that stuff. All right, so let's hop right in. So the early beginnings of calculus. So Egyptians were able to calculate the volume of a frustum of a square pyramid as well as the surface area. This is known by our discovery of the Moscow Papyrus, which was created sometime about 820 BCE. Here's like a little image of the papyrus where we can see the frustum. So the foundations for discovering areas has a history we've known about it for quite a while. We're going to fast forward a bit to Archimedes in the 3rd century BCE. He was the first to find the tangent to a curve other than a circle. And then he's also credited with implementing the method of exhaustion along with Antiphon and Eudoxus. Excuse me. We're going to talk a little bit more about the method of exhaustion in a second. And then there's also Aryabhata. He, in the 5th century CE, he came up with the sum of cubes formula, and he expressed the astronomical problem in the form of differential equation, which led to Bhaskara II to describe an early form of Rolle's theorem. Then we had the sum of fourth powers by Ibn al-Haytham, and then Parameshvara had an early version of the mean value theorem. So all of these were predating Newton. All these may or may not have contributed to it, but more than likely they did. So the method of exhaustion, it was a method of finding the area of a shape by inscribing inside of it a sequence of polygons whose areas converge to the area of the contained shape. Archimedes used it to find a way to compute the area of a circle by filling the circle with a polygon of a greater area and a greater number of sides. The quotient formed by the area of this polygon divided by the square of the circle radius can be made arbitrarily close to pi. This led to the successful evaluation of an infinite geometric sequence. So if you look at our image here, we can see if we start with an area of a pentagram, right? And we have an area greater than it and an area inside of it. We can see the difference of trying to find the area of the circle. We can see the difference of the little areas that hang off the top and the areas that are missing. We are able to find the difference, and we can therefore calculate the area of the circle. As we increase the sides of the polygon inscribed around the circle, we get very, very close to the area of a circle. This led to the idea of the infinitesimal. So we'll talk a little more about that, but you can see how these are the foundations for infinitesimal calculus. Into Greek antiquity, there's a Pythagorean discovery of the incommensurability of lines. However, the infinitesimal was not welcomed in Greek geometry due to the school of philosophy at Elea. We'll talk at the next slide. We'll talk a little more about that. But the most damaging effects was by the philosopher Zeno and his paradoxes. Zeno and his paradoxes basically led to people disregarding the idea of infinity and infinitesimal. It kind of held back the development of the idea of calculus for quite a while. So let's talk a little bit about Zeno. He had a set of paradoxes that. So he had these sets of paradoxes attempted to discredit the idea of the infinitesimal. The first paradox was the dichotomy. So basically, Zeno said, suppose a runner is running to school. The runner must run at least halfway before getting to school. So if we see our little image here, he runs at least halfway. Before he runs halfway, he must run a quarter of the way. Before running a quarter of the way, he must run an eighth of the way. Before running an eighth of the way, he must run a 16th of the way. Before running a 16th of the way, he must run a 1/32nd, 1/64th, and so on and so forth. Zeno then supposed that based on this idea of him infinitely getting closer, the runner never makes it to his destination. And he practices at the school where people, typically agreed upon it. And if that didn't sway people against the idea of the infinitesimal, he also had a similar paradox called Achilles and the tortoise. So in this one, he said, suppose Achilles and a tortoise are in a race. Achilles runs at a speed of 1 meter per second, and the tortoise at 0.1 meter per second. So the tortoise gets a head start by 0.9 meters. It should take Achilles 1 second to catch up to the tortoise. But if one breaks Achilles' motion into sections like the dichotomy, then Achilles will never reach the tortoise, because as Achilles approaches the tortoise just moves ever so slightly ahead. So if Achilles starts here and the tortoise starts here, Achilles moves 1 meter in a second, and then the tortoise moves ever so slightly ahead. Achilles then tries to move up another meter, but the tortoise moves up another further ahead. At this point, the Achilles never reaches up to the tortoise. Lastly, Zeno had the arrow paradox. It's very similar to the other two, but he said, consider an arrow in motion at any instant. In that moment, the arrow travels no distance. So man fires an arrow, it travels no distance. But the entire motion, so he fires an arrow, and then we take a snapshot here. We can see the arrow stop right here. In that moment, the arrow travels no distance. But the entire period of its motion only contains instants. So there's an instant here, an instant here, an instant here, an instant here, an instant here. All of which contain an arrow at rest. Therefore, the arrow cannot be moving. We now know this obviously is not how motion works. But you can see how the idea of the infinitesimal leads to a paradox, which therefore cannot be true. All of these paradoxes set back infinitesimal thinking for quite a while. We're going to fast. So now we have the slow creep towards Newton and Leibniz. As I stated in my other videos, there was the introduction of Hindu Arabic numerals, as well as symbolic foundations for mathematics. In my other video on the history of algebra, if you notice, we talked about a little bit about the universally agreed upon symbolism for algebra. This didn't happen until about the 16th century, 17th century. So there was no really universal mathematical language that people could agree upon until that point. And then Jean Buridan had the idea of impetus, or also the idea of impulse motion. Then we had the cubic equation solution by Cardano. This was also in my video about algebra. And then we had the quartic equations by Ferrari. And once again, that's also in the algebra video. Then we had the more loose use of irrational, negative, and imaginary numbers. People began to generally accept that these are actual terms and not just fake numbers or non-mathematical nonsense. Then we had the introduction of symbolic language for mathematics. Up until that point, we had, as well as Kepler, Stiefel, and Vieta, considered a circle with a polygon with infinite sides through the method of exhaustion. And we kind of covered that earlier in our method of exhaustion slide. And then John Wallis was the first to use a modern infinity sign. And then right up until Isaac Newton, Barrow, Fermat, Pascal, Wallis, and others began to make the later groundworks for Newton and Leibniz. Barrow was actually the teacher of Newton. So they are immediately connected. And then we have Isaac Newton and Gottfried Leibniz. Obviously, these two are the two main people in the birth of calculus. They began developing their calculus near the same time, Newton in 1665 and Leibniz in 1673. Leibniz was the first to publish his work, but Newton is considered to have the first started in investigating the ideas of calculus. At this point, when they were both submitting their work, initial opinions believe that Leibniz had plagiarized Newton. This is due to them believing that he had access to Newton's notes, and he basically copied off of him. And then in 1712, there was a investigation into these claims. They published a collection of correspondence relevant to the dispute. They found in favor of Newton that he was plagiarized. However, this is very murky territory as Newton was the president of the society. So the society had all of his friends, his colleagues, his mentors that were in favor of him. However, as society moved forward, modern beliefs are that they each developed calculus independently, as we'll talk about in the next slide. So Newton's calculus. When he was discovering it, he expanded the binomial theorem through analysis of an infinite series. He then determined the area under a curve by calculating a momentary rate of change. So we're starting to see the major foundations for calculus. In his calculus, the base of it was the idea of continuity or continual flowing motion. He defined rate of change as a flexion. And within his calculus, the fundamental theorem of calculus was built into it. And we can see here that Newton's notations for differentiation was a y with a dot, which was equal to dy over dt. And his integration was an x with a line over it or an x with a box. We don't really see these too much anymore. We'll talk about Leibniz's version on the other second. For Leibniz's calculus, he argued that the integral was the sum of an infinite number of rectangles, Riemann sums. And then we had the infinitesimals were the cornerstone of his work. And then most of the modern symbology that we use are Leibniz's versions. As you can see here, he had df of x over dx or dy dx. And then he was also the first to introduce the integral sign, an elongated s for a summation. And so in calculus, these are the more modern notations that we see today. I hope that this video kind of enlightens a little bit about the history of calculus, and that, like I said, it furthers investigation into this. Maybe these ideas can be introduced into a modern calculus class, help students understand why we use these notations and what these notations mean for exactly. I hope you enjoyed this. Well, I hope you enjoyed this video, and thank you for watching.